Okay. Now we stopped last session with life cycle cost. You know, as engineer, whatever your specialty, you're going to work on projects. Part of the project is not only the technical aspects, the economic aspect. You need to check the cost, your cash flow, cost of energy, payback period, this stuff, I mean, cost effective and so on. So for life cycle cost, LCC, okay, we will focus on the capital cost and replacement cost, maintenance cost, and salvage. You know, capital cost, the amount to be paid at the beginning of the project, replacement when we replace some parts of the project, and maintenance to be done annually. And salvage is when the project finish, the useful parts of the project would to be sale, which means it will be income rather than outcome. I will apply this discussion here in this example. Let's assume that in Faculty of Engineering we want to have to install PV system. Okay. By the way, I gave here example on PV. It could be given for any other type of renewable energy. Faculty of Engineering on the top rooftop, 15 kilowatt hour energy per day. This is the energy from the PV. And he told you in the question that the solar module, this type, the rating is 205 voltage, many information. By the way, information given to you, but it doesn't mean that you need to use all of them. Use the useful one to your problem. The number of modules considered is 16 panel, 16 module. Okay, each one, as I mentioned, 205 watt. MPP battery charger, it means charger controller. This type, this brand. Batteries used are these batteries. Their life cycle or lifetime is 6 years. It means every 6 years we need to change the batteries. Inverter also. And also he tell you the cost for each part. It means, have a look here. The 16 module, PV module, costs this amount in Omani Riyal. The 12 batteries cost this amount. Charger controller cost this amount. Inverter, cable, the frame we use to put the panels here cost this amount. And the cost of installation and commissioning the company when they come to install it, they cost us this amount. And finally, the maintenance cost, it means annually, we pay 200 Omani Riyal. Okay. Now, first of all, I will calculate the capital cost. Capital cost, it means the cost I pay at the beginning, which is the cost of all these components from 1 to 7, all of them included in the capital cost. Maintenance cost is not included because every year I will pay it. So it will not include it. So this is the total amount. And also he told me in the question that the PV panel will work up to 24 years. Batteries 6 years, and then I need to change. Control, charger controller, inverter, cable, all of them 12 years, and I need to replacement. Also, he told me that interest rate in Oman is fixed by the central bank, and inflation rate also are 4%, 7%, and 5%. I call them I and F. Furthermore, he told me also that in Oman, the peak sun hours is 5 hours. Just a minute, what is peak sun hour? You remember the spectrum? This is the spectrum for 24 hours. 24 hours, the whole day. This is the middle of the day, right? Now, from here to here, this part from the spectrum where we have the highest solar insolation, we call them the peak sun hours. See how many hours these. Okay, why? Because we do calculation based on these. These are the best time where to produce a high power, let me say flattened power. Or if he gave me as example here, range from 5 to 5.9 due to the seasonal change, summer and winter, then we select the lowest, which is 5. So I multiply 5 hours daily by 205, the one panel. It generates 1025 watt hour. This is the energy generated by one PV module. If I multiply by 16 modules, then I have this amount of energy generated by the PV system. Now cash flow, this is year number 0 when we start the project. And after 24 years, we will finish the project. Now at year number 0, I will pay K, which is capital cost, K. And annual maintenance cost, AMC, to be paid every year. This is year 1, 2, 3, 4, and so on. So you can see this row represent the annual maintenance cost to be paid every year. After 6 years, I need to replace the batteries. And after another 6 years, which means 12, another batteries. And another 6 years, another battery. I don't need to replace here because the project already finished. At after 12 years, cable, charger, controller, inverter to be replaced, because he told me after every 12 years we need to replace them. This is how the flow of the cash will be through the project. To calculate the life cycle cost, I need to calculate the present worth for each one of them. Present worth, it means the worth, the money for that part. I will pay for that part. Have a look. For capital cost, we already calculate them. I mentioned elements from 1 to 7 has been calculated. Now let's come to the battery. For battery, I have formula. You don't need to know from where it came. It's not our job now. We just need to use the formula. This is a procedure to be applied for any system, okay? You have the cost of the battery, it's given in the question. You multiply it by 1 plus F over 1 plus I. Rises to power 6, the number of the years where you are going to replace the batteries. I got this value. It is lower than the original because we expected with more years, the price is going down. I repeat it again, the same formula, but after 12 years, because I again gonna replace this one. So this is another amount of money I pay. Another 6 years, which means 18, I got another amount. All these amounts represent the present worth for batteries. For cable, charger, controller, and inverter, all of them to be replaced after 12 years. So since they are to replace after 12 years, I will add them. I call them C, the cost of all of them, which is charger, controller cost, cable cost, inverter cost. I multiply it by the same formula rises to power 12, because after 12 years I will change them. So this is what I got. Now, for maintenance, the formula is different here for maintenance. We have different formula as you can see here. It is AMC 1 plus F over I minus F, 1 minus 1 plus the same previous formula, rises to power 24 to tell you that it will continue for 24 years. So this is the maintenance cost. For salvage, it means at the end of the project, what is the useful part to be sold? Okay, we have the panels, they recycle them, and we have the frame because it's metal. So salvage will contain the cost of the panels, original panels, plus the frame, rises to power 24 here, because after 24 I will sell them. This is the amount. By the way, salvage is return. Let me back. You see here, salvage is a row in the opposite direction. It means this direction I pay, this direction I take. Now let's find the life cycle cost. Life cycle cost represent all previous present worth, adding them, minus the salvage. So I substitute, as you can see here, I got this amount. This is the total amount of the life cycle cost. But still, I need to calculate the cost of energy. So to calculate cost of energy, what I will do, I will use this formula, which is called annual life cycle cost. I divided the life cycle cost, which is already calculated here, by this substituting this formula. I got annual life cycle cost. By the way, you can try it when you have time. Try to do the same calculation. Now, this is the annual life cycle cost. I will divide it by 365 days by the total energy calculated at the beginning. What I got? Cost of energy. it's fine that it cost me 0.144 Omani Riyal per kilowatt hour. So every kilowatt hour will cost me around 15 paise, 150 paise, sorry. Now for life cycle analysis, I discussed the life cycle cost, Now life cycle analysis. Life cycle analysis simply is the impact of my project on the environment. I want to assess it, evaluate it, test it, okay, to see what is the impact. Through the project, yeah, from A to Z. It means from when we took the raw material from nature, we introduce it to product and convert it into something artificial, then we use it, then we recycle it, then return it back to the environment. All these cycle is important to be known. I mean, you understand that as an engineer, you will solve problems at the end of the day. And these problems to be solved technically using the approaches, method, techniques, theorems you already have experience with them. But this is not enough. You need to add to this technical the cost or the economic side of you and the environment side of you. It become a must today. You cannot ignore them. You need to add them here. So for economic, we just discussed, we give example here. By the way, there is a lot of to be said here, but we don't have time in this semester, as you know. But at least we know how to find the cost of energy, the life cycle cost. Now for the second part, which is life cycle analysis, what we have different technique and methods. There is no clear, let me say, flow chart you can follow with this detailed step because it's related to each project. From project to project, there is differences. But there is some tips could be followed. As example, goals, put goals on the scope for your impact, the environmental impact in your project, and put the assumptions, the parameters, the boundaries or constraints. Then identify the input and output. What is your input? You start with what is the output you will gonna end with. Then check the impact, analyze the impact in each stage of the project. And then you do assessment and judgment at the end. These are just tips you can follow in general. Otherwise, for each project, there is different case and you have different assumptions. Now, last part here to be discussed is the geothermal energy. We discussed different type of energy. Geothermal energy is the energy under the ground. You go deeply down under the ground, you find that the heat increase. And we can see that these geothermal, let me say, lava and gamma going out because of either it's going out as a hot water, steam, hot air, let me say, rocks, hot rocks, and so on. We can see something similar in many places in the world. As example, here in Oman, if you go to Nakhal or Al-Rustaq, there are some hot water there. عين ثوارة, عين الكسفة, and so. These are available and there's a huge amount of energy can be extracted from them. We can use them for different applications as we will discuss through this part. As you can see here, you go deeply down, okay, this deep in kilometer to the center of the earth, you can see the temperature rises, huge amount of energy is there. We just need to know how to extract it. Use it. This is called a geothermal reservoir. You see here, the rocks here are warm. When it gets rain, leaves the water going down and get warm and going up again as a hot water or let me say steam. Sometimes if there is no water here, it's not coming from rain, we can do something, provide water or some other fluid to bring this energy from down the, let me say, the surface of the earth. And by the way, you know, animals usually what they do, they try to use the surface of the earth, close to the surface, and they try to hide there, searching for air conditioning through seasons. As example, rabbits and rats in summer when it's warm, they go under the ground because it's colder than the outside surface. And in winter, the opposite. They go under the ground because it's warmer than the outside surface. Geothermal reservoirs could be used for many applications. One of them, and important one, is generating electricity. You can see here. This is here as example. How this is normal thermal plant. Rather than we burn fuel, oil or gas or wood or coal or whatever it is to provide heat. Heat is already there under the ground here. This is the reservoir. We take the hot water here through the heat exchanger. There is a fluid inside. It vaporizes, produce steam, rotate turbine, generator. We have electricity. Very simple, traditional plant. Just the heat coming from the underground reservoir. Now this is all data, but I would like to say through this data something. Here, this is 2003 United States energy. See the energy profile. 23% coal, 23 gas, petroleum, nuclear, and only 6% renewable at that time. This 6%, if we break it down, we will find solar, biomass, geothermal. You may say, okay, solar 1 or geothermal 5 or 2, what is the benefit? It's a very small fraction. No, we should not deal with energy profile in this way. We should deal with energy profile in the way that we diversify our resources. We use our resources available in nature, our nature. We don't need to bring the solar from outside or the geothermal or the wind. It's there available close to our homes. So why don't we use it? We have to use it. Heating pump, let me say, or cooling for heating or cooling, geothermal pumps use here to do air conditioning, cooling or heating. You see, this is the house, a network of pipes. Here you can see these pipes, some of them red here or blue. Red, it means hot water in this side, and blue water, it means, sorry, cold water, the blue part. And we try to, either if it is winter, we need heating, so water will go in this direction. If it is summer, we need cooling, water will go in this direction. So we can use it for air conditioning. It's used by many countries. Just it is not being used by people here because there is no market for it, because people, they don't know about it. And don't forget that we have heat exchanger. We need to use heat exchanger in this type of system. It's better to use heat exchanger in this type of system. Pump, we need to rotate the water. But this geothermal pump is used in many countries by circulating the warm water or cold water in different way. It could be vertical, horizontal, from well to well, from bond. I will give example here. Have a look. This is a house. I want to use the geothermal reservoir for air conditioning, heating in winter, cooling in summer. And the reservoir is vertically. If I dig deep vertically, I can't find the reservoir. Then the pipes to be vertical in this way. Vertical pipes. The water follow these pipes. Here the heat is get heated and back as a hot water inside. We use it in one way or another. Sometimes it's close to the surface. We don't need to go deep. We go close to the surface, which is called horizontal. Okay. Sometimes there is two wells. Okay, we can use them for cooling or heating from one well to another well. And also, sometimes there is bond. We try to use, as example here, we let this part close to the surface so it get warm water. And here we reject the part here down deep in the pond for the cold water. So use the heat available under the ground, under the surface crust to heat or cool our houses. Geothermal power plant, as I mentioned, it is similar to the conventional thermal power plant. But rather than we burn fuel, we use the thermal energy available under the surface of the earth. Different, let me say, power plants are used there. It could be flash type power plant, dry steam binary power plant, flash binary power plant. Let me take them one by one. Flash power plant. Flash power plant, what happened is we brought the water from the reservoir, warm water, and here we're gonna split the warm water and return back to the reservoir. We take only the steam. For that we call it flash stream. We took only the steam. It rotates the turbo generator to generate electricity. So split hot water from the steam. The second one, dry steam. Dry steam, there is no separation between warm water and steam because there is no warm water. It's only steam coming out. Only the reservoir type is steam type. You can see here steam coming directly. No need for separation. This is power plant use the steam directly. And this is here a larger picture. You can see photo. You can see the steam going directly from down up and rotate the turbine. Binary power plant, sometimes we have temperature lower than even 100 degree Celsius. The water cannot convert it to steam. So if the temperature is low, which cannot be used to get steam with high pressure, okay, even more than 150, we go for binary. Binary, we are gonna use heat exchanger and the fluid which can be liquidized, vaporized with low temperature. Example, have a look here. This is the hot water coming here, heat exchanger. Inside this part, the second part of the heat exchanger, we have another fluid which can be vaporized, converted to vapor with low temperature. Then we rotate the turbo generator here and condense and back. You see this binary. And by the way, just to mention that I remember the study reported by Authority of Electricity Regulation 2008, the report I mentioned in some of my lectures. Their recommendation regarding geothermal, there is no potential and the temperature is low, which is not suitable to generate electricity, and which is not, accurate, because the accurate issue is there is binary systems that can use this low temperature to generate electricity. Now, flash binary, it's from the name, it's hybrid. It's used both for a flash, okay? Remember, this is a flash. Just to remind you, we separate warm water from the steam. Binary, we use heat exchanger. Here, I'm gonna do the same, both of them, okay? Sorry, this one. I'm gonna here, as you can, split the warm water here and take the steam to rotate, okay? And this is the at the same time heat exchanger. Rotate here back to here to reheat. It's similar to the reheating of thermal power plant. So I use both cases. Now to enhance the geothermal system, what we are going to do, we are going to use water, okay, even water, brackish water, or let me say water which is not used for drinking or not fresh water, any clean water, but we inject it under the ground to the rocks. Whenever we find the reservoir as a rocks, we will start using water injected under the ground to get the warm water. Example of the technology invest in this is in 2009 by Kalina, one of the European companies. They use ammonia with water, both, okay? Water from one side, ammonia from the other side for the heat exchanger, and then they produce heat used for different application. By the way, it's not necessary to be used only for electricity generation. We may use it for another application, as example, air conditioning. Distribution generator, you know the electrical grid, okay? These are the wires taking the electricity. Sometimes they put generator, okay, to support the grid in some places, okay? They call them distributed generator. In different, let me say, after every few tens kilometer or hundreds kilometers, they put DG. They call it distributed generator. The availability of geothermal could be used for small generators as a DG, We don't need to use the generator to provide electricity for a village or a city. No, but as a DG, since it's close to the network, why don't we? So this is give it a credit for geothermal. Now, supercritical cycle, next week, inshallah, which is week number 13, the last week, and we're gonna finish the syllabus. I will talk about climate change, global warming, and its relation to energy, and we'll talk about carbon. We will have a good discussion about carbon dioxide capture, storage, utilization, and so. So, carbon dioxide, usually they capture it and store it sometime under the ground. So part of the application is we can use it injected under the ground to make a reservoir. There is rocks there, but we need to drill, similar to the oil drilling. And then we inject the carbon with, we may mix the carbon with another, let me say, fluid, okay, for enhancement. But when we inject it down, we want to create a reservoir, useful reservoir. This is what we call it a supercritical cycle, one of the application of using carbon dioxide capture and storage. I will stop here for this on this part.